All right, 7:20. So I think we should start. So you guys hear me at the back, right? Yes. Okay. And online, can you guys confirm hearing me? Anyone online? Hello? Can
Yes,
you
we
guys
can hear you.
You can? Okay, very good. And you see my screen too, right?
Yes.
Very good. So as I said last time, I'm not monitoring the chat that often while I'm teaching because my screen is very small. So anytime you guys have a question, just speak up, right? There's not that many of us. And so you can interrupt us very easily without any problem, right? And the same thing over here too. If you ever had a question, just like do this, and I will ask you to ask the question. All right. So what did we do last week? We basically spent last week showing what are different kind of energy conversion method that we use currently, right? And in the second part, we start talking about turbo machines, things that are rotating, like pumps and turbines and wind turbines. And we said that eventually the exchange between the fluid, whether it's water and air, and the machine involve angular momentum, right? So for example, over here, this is a hydraulic turbine. The rotor is the guy that's rotating. And in case of the turbine, we call it also the runner. The rotor and the pump is the thing that's also running around. And we call it, in case of the pump, the impeller, right? And say in the submarine, the thing that's rotating is a rotor, but we call it propeller. So those are names for the thing that's rotating. There is something rotating, that's the rotor, and there's something fixed, not rotating, and that is the stator. And if I jump just a bunch of slides over here, so I'll show you. Maybe this is a good picture. So you can see how this is again the rotor, and in the case of a turbine, we call it the runner. So that runner, in order to turn, someone need to give him angular momentum. Someone need to give him things that's rotating, a fluid that's rotating. And so when you think about it, water is dropping from a high elevation to a low elevation. That's how we are turning or making energy, because we have a potential energy. We build a dam, we raise the water behind, water in front is low, and that rho GH, that difference in pressure, or the GH, the energy per kilogram, joule per kilogram is GH, right? So that potential energy is what are we trying to extract, okay? The GH, where H is what? The height between this point and that point, that would be the H, right? So GH is the joule per kilogram. So if you want to find out, so how many kilowatt, how many megawatt, when those big dams with big turbine can actually generate gigawatt of energy. So it could be like as big as one power station like Jinx, that's almost like 1 gigawatt. You can get this from a bunch of turbine, hydraulic turbine too. So how can I get my kilowatt or megawatt from this? You need, this is joule per kilogram. That's the energy per kilogram. So I need to multiply by what? By what exactly? So I can get the power. I need to turn joule per kilogram to joule per second. What do I need to multiply with? Kilogram per second. Excellent. Pebin is saying kilogram per second. That's m dot. So m dot GH, that would be the power you expect to extract. Ideally, if there is no losses, if the flow go into the pipe, into the turbine without losing anything, no friction, no circulation, no separation, no eddies, that's the maximum power you will get. Of course, the real power you need to multiply by some kind of efficiency. This is my eta. My Greek is my writing anyway is horrible, whether it's English or Latin. But anyway, that's my eta. Okay, so you multiply m dot gh time the efficiency eta, you get the actual power you extract from the turbine. But what I'm trying to say over here is that although the source of energy is potential energy, and in the case of a wind turbine, what is our source of energy for a wind turbine? What do we what? Kinetic energy, right? So kinetic energy in case of the wind, right? So let me get my doodling page. So in case of a wind turbine, here is the tower, here is the plate, and those plates are huge, can reach like 50 meter, 100 meter. So again, what is the source of energy? Kinetic energy. What's that? Half V square. What is the unit of this guy? Half V square. It's the easy answer, of course, is meter square per second square because it's the velocity. But the hard answer is joule per kilogram. How come? Because what is kinetic energy? If I throw this pin and he's flying and you're trying to calculate his kinetic energy, you would say half mv square. Isn't that the kinetic energy? Half mv square. So the energy per unit mass is the half v square. Take out the m. So now when we look at those big turbine on the highway, and you'd say this guy is 2 megawatt turbine or 1 megawatt, how do you get the power from this? What do you need to multiply with? M dot, kilogram per second. So again, the m dot multiplied by half v square, that would be your power, your megawatt or kilowatt or whatever this number is. And how do we get m dot? What did we say about m dot last time? Rho, here of course, multiply by, what's m dot? Help me. Rho time, someone asked you to calculate the m dot of the air coming toward this thing. How do you calculate the m dot? Excellent. Rho AV, right? So the m dot is rho AV. All right, so what I'm trying to say then, whether the source is kinetic energy, like in the wind, or potential energy, like in this water sitting up here with almost no velocity, because the V here is, almost zero. The water is just sitting and you let it drop. But at the end of the day, when the energy actually exchange from the fluid to the metal, it's kinetic. It's basically the tangential moment, right? So how do we spin the fluid so that he can spin the shaft? It's the stator part, okay? So that is what is drawn by this. Those plates are the stator. Those are the one that will spin the fluid before he come in so that he can hit the runner. And in today homework, so you're gonna have an official homework today, your first homework, he will ask you about that angle. What is the angle of the plate of the stator? So that he generate the velocity with the right magnitude, right direction, so that he can spin your turbine for you, okay? Sometimes the rotation or that initial momentum is generated very easily just by, look at this. Here is the water tube coming from, say, 100 meter or whatever the elevation is. Water is rushing because of what? Because of this, right? When you drop the water from a very high height, by the time it comes down, ideally the speed should be If I'm dropping it from H, what's the ideal velocity? No losses whatsoever. What should you get? 2gh, square root of 2gh, right? Square root of 2gh, how did I get that? Half v square plus gh is constant. Joule per kilogram, joule per kilogram. Half v square plus gh is constant. So here you have potential and you have zero velocity. Here, by the time you come here, you have zero potential. Why? Because I choose this datum to be zero. Doesn't really matter. It's the difference that we care about. And here I have kinetic energy. So this half v square by the time he come here is equal to the gh, right? So by the time the water, let's make the water over here like this. The water is dropping from this big dam. By the time it's come here and it's ready to hit my turbine, that V idly, without any losses, will end up being square root of 2gh. How did I do this? Because if I do Bernoulli equation between point 1 and point 2, I would say that gh plus half v square equal constant. Of course, assuming no losses. If there is losses in the process, then fine. The initial energy equal to the final energy plus the losses. So the losses eat a little bit from the output. So doing this at 1, you would say gh1 plus 0 equal, and let's choose this to be z equals 0. No potential energy at the floor. Then this will be equal to half v2 square. And so it's very clear why the velocity then will end up being the square root of 2gh ideally, right? Of course, if the pipe is not really that big, and if the pipe roughness is really a little bit large, one could expect that, you know, this is gh is half v squared plus bunch of losses, right? And actually, for the convenience of this equation, which is written in joule per kilogram, they will express the losses in the pipe in terms of H also. They call it the head loss. So they will call it GH loss. And they will tell you the losses in this pipe is like 4 meters of water. So you have like a dam that have, say, 50 meters behind, and the piping and all the kinks and the elbows and stuff is like 4 meters or 5 meters. It take from the actual head available to you, right? And if you guys remember from your fluid 1 course, how did we calculate this H loss in pipes and elbows and valves and stuff? If I have something like this with a valve, even if it's partially open, it still have losses. And say 90-degree elbow and then a pipe and then 90-degree elbow and then another pipe. If someone tell you, well, what is the H loss in this system? What do you do? How do you write? What's the equation for it? Yes, yes, that is exactly right. Sigma K elbows, and that's other elbow, and that valve, and what kind of valve, and is it open or not, and maybe you have a screen here to prevent the fish from being shredded and become tuna salad by the time they go in. So all those K's are added. This is my sigma. Okay, sigma is like you add all the losses. Sigma K plus what about the straight section of the pipe? L and L1 and L2, and what do we do with all that, guys? All those lenses. We say FL over D, where L is the length of the pipe and D is the diameter of the pipe. And all this is multiplied by V square, ouch, V square over 2G. Can I make my V better? Right? And remind me, how do we get the F? That friction factor, how did we do that? Does anyone remember? Pipe flow. Yes, Reynolds number on the x-axis, the F was on the y-axis, and there was one curve over here, and there were a bunch of curves for different, what were those curves for? Anyone? Like we used to go with the Reynolds number, get one of those curves and say, our F is 0.01, for example. What are those curves are for? And more important, what is this chart? This chart has a very famous name. Excellent. Excellent. This is a Moody chart. And you should remember then what was those curves are for? Why there were so many curves? No, the laminar is this range, which was the Reynolds number less than 2,300, and the turbulence was for this range, which the Reynolds number is 4,000. But what are those curves are for? The x-axis tell you if you are to the left, that's laminar. If you are to the right, that's turbulent. But those curves were for different, not just pipe. The diameter is correct, but there was also epsilon over d. That was, what is epsilon? Anyone? What's epsilon? Roughness, exactly. And usually there is a table, and that table, is it like really PVC pipe, very smooth, or is it concrete, or is it cast iron, or is it cast iron that has been in surface for so ever, and it's so rough and so once you figure out what's your pipe, once you figure what's your pipe and what's your Reynolds number, which by the way, what's the Reynolds number? Rho multiplied by V multiplied by the diameter divided by, help, what's the Reynolds number? The most important thing in fluid mechanics ever. Mu, the viscosity, correct. That's my mu. Rho Vd over mu, that's the Reynolds number. So you know the velocity that allow you to calculate the Reynolds number, that allow you to calculate the F, and that will allow you to calculate the losses. And then you tell yourself, okay, so here is the turbine, and here is the big dam holding the water, and here is 0.1, and here is 0.2. You will end up telling yourself then the GH1 is equal to half V2 squared plus GH loss. And that H loss is calculated from what we just said. Let's call it L loss so that we are not confused. All right. So then that V2 is the kinetic energy that will have to be, I mean, it's nice that he's moving fast, but if we shoot it fast in the turbine, he will break the turbine and we are not going to get any spinning. So now we need to shoot it with, in this is called Belton wheel. And it's just a bunch of pockets. And he's shooting the jet not in the pipe or sorry, on the turbine, but tangentially to the turbine. Why? Again, he want to generate this kind of angular momentum, right? So in this coordinate system, the velocity, any velocity, if the velocity is coming like this, for example, can be split into two components. The tangential component, and that's the one that you love, and radial component. And you think, well, it's totally wasted, you know, like, no, sometimes it's important to have radial component because that's the flow rate in. In this Belton wheel, it's specifically, I mean, it's a little bit different because the water can come and just drop at the floor. So it's like 3D, not really 2D. But in 2D, like all the other rotors, the only way the flow will come is by the radial component. In order for the flow to enter, we need to enter with the radial component. Okay? And he spin with the tangential component. So I like you to be very comfortable with splitting the velocity because the homework depends on this. The fact that when you see V1 coming like this, you will be able easily to split V1 into two components, and you would call that V1 theta. And in our book, he called it V1 U, not V1 theta. Why V1 U? We said last time because that is U1, which is omega R1. And if this is the exit, that would be U2, and that's omega R2. And what's omega? It's the rotation, radian per second. And what's R? Obviously, R is, this is R2, and this is R1. So because U is the tangential velocity, and he thinks he's splitting V in the tangential direction, he called it V1U. So when you see it in the book, V1U, he means the tangential component. Okay? Now, also, most turbo machines book, they call this angle alpha. The angle that the absolute velocity V1 make with the plate is called alpha. Okay? So in the homework, he say, what is alpha 1? Is there alpha 2? Yeah. Well, you need to look at what is the exit velocity. And if V2 is, for example, like this, which would be bad design, what's the ideal V2? If you're a really good designer, you make your V2 tangential, radial, or like between. And think about what's the purpose of this turbine. The purpose of this turbine is to extract all the angular momentum from the flow. So ideally you like V2 to be, right, you want V2 to be radial. You want to take every angular momentum it got. Okay? So you will see he will come with big V1, sorry, big V1 theta. He will come with big tangential. And how did he do this? Because of the stator, right? Because of this guy that's having his plates like this, and he's ready for the spinning. He is preceded by a stator, plates that are not rotating. But what do? The water come toward them. Actually, it probably be like this. I'm not doing a good job. So the flow would come radially like this, and he will leave with a spin. Okay? Let me try to do a better job. So imagine the flow's coming like this, and we need him, by the time he go into that small rotor, we need him to be spinning. So we'd like him to leave like this. He need to come like this, because he's dropping from the chute, all radial, and he need to leave with a twist. So the ideal plate would be like this. I open it up. And you see, I'm trying to do two things over here. What I'm trying to do. First, I'm trying to make this like really rounded, not sharp. Why? Because yes, the flow is coming radial, but you know, you should allow for a little bit of disturbance. You need to make it a little bit forgiving. When you come like this, he can go, he can come like this. So you don't make it like, it's not razor sharp where you have to come like this, otherwise we will be in a disaster. No. And the second thing I'm trying to do is this is V2 exit, and I'm trying to align this direction with it. Because that really, this angle is what will determine the exit direction. Right? So, but we shouldn't call it V2, we should call it V1, because that is actually V1 for the rotor. So maybe we should call this V naught. So V naught before the stator, V1 is after the stator, which is the inlet to the rotor. And so now V1 will be coming like this, coming like this, coming like this. And for each of those cases, you can see how this V1 can be split into V1 theta and V1 R. Make sense? And that V1 theta is the one that we care about, because the equation for the torque is all about this V1 theta. The torque is m dot R, right, 2 V theta 2 minus R1 V theta 1. So without building that V theta and going into the machine, you will not be able to get a torque. And the power of that turbine, the kilowatt or megawatt, like how big, or gigawatt, how much power you're going to get from that turbine, is torque multiplied by omega. Like any shaft, if you have a torque and he's rotating at certain RPM and someone asks, what's the horsepower of that motor? You would say torque time omega, and I can measure the torque on the shaft. And you multiply by omega, that's the power, right? So imagine if we, now let's multiply omega by this equation so that we can get the power. What do we get? We get the m dot and then R2 omega V theta 2 minus R1 omega V theta 1. What did I do? I just multiply omega everywhere. You wanna call it omega 1 and omega 2? Huh? Do we call it omega 1 and omega 2? Excellent. Omega is the same. Omega is the RPM of this thing, and actually we use radian per second. There's no such thing as omega 1 and omega 2. But there is something like U1 and U2. So although it's the same omega, but you combine those two guys together and you combine those two guys together and you get U2 V theta 2 minus U1 V theta 1. Okay? And so our book have this equation for the power. So when I was undergrad, personally, I just didn't like this equation. I felt that it's kind of like forced, like why do they even need an equation for it? Because I always thought that I know this because of many courses, not just fluid mechanics. Torque time omega, that's the power. And I know this for turbo machines. So my mind cannot handle an extra equation. So I'm not going to even memorize the third one. It does not exist for me. And the dilemma was because we didn't have open book. That's why. So you really had to work in your memory, and so there's not that many space. So you just I have two equations, I'm done. I'm not going to memorize the third one. But since we have open book, and also because why this one, I changed my mind when I became a professor. No, this equation is good. Why? Because sometime he does not ask for the power. So again, the unit of this would be watt or kilowatt or megawatt. Sometime he asks he show you an impeller with the angle and everything, and he tell you, well, how many joule per kilogram does this turbine extract? And what is the unit of the torque? Newton meter. What's the torque of the power? Watts. So where is that joule per kilogram? How can I do that? I divide the power over. If in order to get the joule per kilogram, we divide the power by what? By m dot. And that's why this equation is really helpful. Because when you write the power per m dot, you get yourself U2 V theta 2 minus U1 V theta 1. Okay? And that would be joule per kilogram. So then now I respect this equation because I'm gonna, if I go the other route and tell myself, no, let me calculate the torque and let me calculate the power and then divide over m dot, why? Here is the power per m dot directly. And so you look at this equation, power m dot, and you realize that it's all about velocity. It's the velocity triangle. We call it the velocity triangle. So when you just look at that impeller, okay, and you tell yourself, I got my V1 over here, and here is my V2 over here. All you need to do is to split V1 theta. Actually, maybe we call it V theta 1, right? That makes sense. V theta 1 and VR1. Okay. So by VR, I mean V radial. This is confusing because in our book, VR sometimes he means V relative. Okay. So that is a source of confusion. Most books, however, use this. VR is V radial. And for relative velocity, they use W. Or, I mean, if we just want to be super clear, we can just write V relative. Okay. So we will see in the examples how we can calculate V relative, because we will need it. Let's see, we'll see some example how we can calculate those velocities. But I just need to now everyone should be comfortable with the terminology we are using. V is velocity, absolute velocity, right? V theta is the tangential component of the absolute velocity. VR is the radial component of the tangential velocity. U is the plate velocity, the control volume velocity, the metal velocity. So you got yourself U1 and you got yourself over here U2. Okay, that clear? What is U and what's V? So what is the relative velocity then? Relative velocity, not radial. What is the relative velocity? We said the equation last week was V equal W plus U. That's the equation. Okay, or if we want to be super clear and no confusion whatsoever, we will tell ourselves V absolute is W, which is relative velocity basically, plus U, the control volume velocity or the plate velocity. Okay, so in that sketch in front of us, when V1 was like this, and you got yourself U like this, where is W? Where W or relative velocity? When you add it to U, you should get yourself V. So how do you do this? Well, if we make U here is U1, then that would be W1. Because you add W plus U equal V. And some students get confused when they add vectors. So if you give them vector A and say vector B, and tell them add them, tell me what is C, which is A plus B, they get confused. Okay, and so how do we do this? You need to bring that B over here. Huh? If you bring him over here, that will become your C. So A plus B equal C, right? Very good. So W1, we're just moving it over here. This is W1. So what did we call the angle that the absolute velocity make with the plate or with tangential direction? Alpha. And the velocity, sorry, the angle that the relative velocity is making, we call it beta. Make sense? So let's draw this a little bit clearer for you. So if I have an impeller like this, And here is my V1, and here is my W1, and this is the tangential direction like this. This would be called alpha, and this would be called beta. And the difference between those two guys, between the absolute and the relative, is U, U1. So you can see U plus W equal V. Okay, so now what is really amazing, at least that's what I thought when I was undergrad, is the plate of the rotor should be based on what velocity, V or W? If I want to draw a plate that will take this water nicely and turn it around, that plate should be based on W. This is actually very hard to imagine because people think, well, aren't we shooting with V? Isn't that the truth? Yeah, the truth with respect to someone that is static, someone that's standing. But as far as the rotor is concerned, he's rotating. So you should actually base it on this. So the impeller plate would be like something like this. Because he's not waiting for V, he's waiting for W. Okay? So we know the angle's name, huh? We know that relation between W and V. And we figure out that the last thing I want to say is that it's all about unspinning the fluid. The stators, the guys over here, the stator will spin the fluid for us, and the rotor will unspin this guy and extract the tangential momentum from him. And you get yourself the torque, huh? M dot R2 V theta 2 minus R1 V theta 1. So V theta 2 will be 0 if the flow is all radial at the exit. And you get yourself all the R1 V theta 1. That's what you will harvest. Make sense? Okay, very good. So then what would be really confusing, it should be confusing for you right now, is the rotor of a wind turbine. That's very confusing because when the wind comes toward the plate, does it have tangential component? When the wind comes toward the plate, does it come with tangential component? If I tell you this is 1 and this is 2, 1 is approaching the tower, 2 is after he goes through the rotor. V theta 1, how much is that? Wind is coming toward you, huh? V absolute is all axial, right? Axial, because that's the X of the machine. The wind is coming toward you. Imagine you are sitting on a turbine and the wind is coming toward you. Does it have a tangential component at the inlet to the rotor? No. Why would it come? Like, it's not going to come like this. It's not a tornado approaching us. Just wind blowing on us. So V theta 1 is 0. So if in case a wind turbine V theta 1 is 0, how is it going to generate any torque? Is this equation wrong? Did I screw up in the equation? No, the equation is correct. So then how is it going to generate torque? When it leaves, V theta 2 then, in the case of a wind turbine, is going to have a twist on the opposite direction. See, you can generate, let's talk about linear momentum because it's easy in our head. I can kick my screen, and that's giving a linear momentum, right? When in my way in, I could kick it, but also in the way back, I can just, I used to play taekwondo when I was a kid. I used to make a really good, but if I kick the other way in my way back, you will also move forward. but I'm kicking him backwards. So what I'm trying to say is that if you have a rotor like this, and this is hard to imagine, but if the wind is coming in that direction and leaving with that direction from the plate, so it's coming all axial, huh? This is the cross section, like looking from the top. What will happen? The plate will move this way. So here is 1 and here is 2. And v theta 1 is 0, but v theta 2 is not 0. So when you write this equation, torque is m dot r1 v theta, sorry, r2 v theta 2 minus r1 v theta 1. So although this guy is 0 at the inlet, but this one is not. And this one will carry the day. So then the wind leaving a wind turbine in the back, it will be spinning the opposite direction of the rotor. It will be going this way, pushing the rotor the other way. Right? And the equation is always valid. Very good. So back to our business. So all this just to convince you that whether you are turning kinetic energy or turning potential energy, at the end of the day, the rotor will do this by spinning action in it. That's why they call it turbo machines, because they rotate. Very good. Now, something interesting is happening too in this drawing. This, look at the cross-section area here and the cross-section over there. This is called draft tube. And so hydraulic turbine, at the exit, they have like a tube that gets bigger and bigger and bigger. Why do you think the area is getting bigger and bigger and bigger? Excellent. Excellent. So that they make this velocity really small. And when you think from Bernoulli point of view, when we say GH1 plus 0 equal, so now if this is my 2 actually over here, I would say the GH1 is gonna be GH2, which is 0, because that's like the exit, and we will choose this Z to be 0, plus the exit velocity, half V2 squared, and that's why you can see that it's in your best interest to make this as small as possible, plus GH loss, and also it's your best interest to make this as small as possible, plus what? Huh? What I'm circling? What am I circling over here? I'm trying to circle the rotor. When it comes to energy, doesn't this rotor do something for us? As far as Bernoulli is concerned, I give you that energy over here, and at the end, you wasted your energy in what? In 3 things. Exit kinetic energy, you want to slow it down. Losses in the pipe, you want to make your pipe and corner as smooth as possible. And what is the third thing that we spend our energy on? Turning the turbine. That's actually useful. But from Bernoulli equation point of view, this is where you spend your money. So this is very nice, interesting. Actually, you're going to see that they can express the turbine work in terms of H. So they can call it H turbine or H useful. Or so again, what is this head? Well, it's again when you multiply by G, that's the joule per kilogram that the turbine has been extracting from you, which happen to be, what is that GH turbine? U2 V theta 2 minus U1 V theta 1. Remember the joule per kilogram thing? U2 V theta 2 minus U1 V theta 1. That's actually this guy. But then this is your Bernoulli equation, right? So it's very clear why do you wanna Why do you want to slow down your V2? Not just because of Bernoulli equation, but also because if the V2 at the exit is very large, that can erode your bed and problem too. Okay, but one of you shouldn't be happy. One of you should question this equation. Something should make you uneasy about this. What is making you uncomfortable as an engineer in this analysis? Is there anything that's wrong with or confusing? If I were you, I would say, well, okay, I understand that you apply Bernoulli between 0.1 over here and 0.2 over here. And I can see how this V2 getting smaller make Bernoulli equation happy because you will have more available for this, right? But I don't really see how does this affect this turbine. How does this velocity over here getting smaller or bigger make this turbine where the actual action happened any different? So the question for you for a free homework problem, if you answer this right, you don't have to do your homework. Get full mark in the homework. Why does changing that V2 will really make the work of this turbine more? Okay, so basically, how does this Bernoulli equation, which is for the whole box, work at the rotor? How does the turbine rotor feel it? If you know the answer, you email it to me today after the class, and then the first person to answer right, he will get a free homework problem. All right? You understand the question? Like that big control volume analysis tell us V2 is useful for extra work. But as a rotor, imagine yourself as a rotor over here, why would I even care? How does it trickle down to me as a rotor and make my work bigger? The fact that the exit pipe is a little bit more. Okay? It's something along the line of like, how if the professor had a very good lunch today, how would that even affect me in the class? Well, maybe if you have a very good lunch, you'll be happy, you'll come to the lecture, and he will explain a little bit better job rather than if you have a really bad lunch. So something along this line. What happens if V2 is really small? So what? What does that do to me as a rotor? Okay. Very good. But that Lambert analysis, or the control volume analysis is very useful to estimate not the turbine plates and angle, but how much power you should expect. And so this is the equation that we just wrote. Okay. So what is this gamma? Anyone? What is that? That is rho G. So why? Because Bernoulli equation can be written. Bernoulli equation can be written as GH plus V square over 2, P plus B over rho plus GH plus V square equal constant. But you can also choose to divide over G, and then the equation become B over rho G plus H plus V square over 2G equal constant. So what unit is that? That's in meter. So rather than joule per kilogram, you can actually write it in meter. And so that equation that we just wrote for the dam in that unit would become H1 equal H2 plus H loss plus H turbine plus V2 square over 2G. Okay, and H2 will go to 0 if you choose that the dam exit over here is at z equals 0. So if you choose this to be z equals 0, here's 0.1 and here's 0.2, and you tell yourself, well, this is h1 and this h2 is 0. Right? Make sense? So you can write Bernoulli equation in joule per kilogram, or you can write it in meter. And sometimes it's useful because people are used to see that, say, what's the H loss of this piping system? What's the head loss? We call it the head loss. And then you can express also the turbine in H. And so you can see then, well, if I have 60 feet or 60 meter dam, you know, how much is going to be, how many meters are lost and how many are turbine useful, and how many is going to just be kinetic energy that we just have to lose at the end. Okay, the third, what's the third way to write the Bernoulli equation? You can write it in joule per kilogram, or you can write it in meter, or you can write it as any other way. Have you seen it in fluid one? They can write it in pressure. They can just say P plus half rho V squared plus rho GZ equal constant. And so that's, of course, in Pascal, Pascal, Pascal. Right? And why my pen is so... I have to make it big. Okay. So B over rho G is basically in meter. That's unit of head. And V squared over 2G and the Z equal the exit plus the losses plus the turbine. Okay. I thought that this should have been H turbine. What's going on? Well, the W is the joule per kilogram, and then so it's like basically GH, and then he's dividing over G so that he can get with the H. So it's a very complicated way to say H. Okay. And what's with the GZ? That's when you gonna GC is to correct for you not using slugs. If you use pound mass, which is wrong, but you fix it with GZ. Okay, so we are not going to use the GC. We're going to stick to SI, and things would be just fine for us without GZ. GZ is for people who mess up and use pound mass, so they have to correct for it. So I strongly recommend throughout your career to always use SI unit like Newton. Let me use, what is, give me a bigger pen, man. Okay, this one. Newton, kilogram, meter, okay? And you use pound, you use slug, and you use feet. No inches, no pound mass. If you do this, your life would be much easier. Okay. So again, that Lambert analysis help you to figure out how much the turbine should extract. And that's detailed analysis where you do the velocity diagram and stuff. That's to get the actual angle. But just with putting one control volume over the whole thing, you can basically tell yourself, I think this turbine is going to give us 2 gigawatt or 1 gigawatt or 100 kilowatt. And then the fluid mechanics guy come and design the runner for you with the right angle so that you can really get that 2 gigawatt or 2 megawatt or whatever the number is. Okay, very good. So this is nothing but just saying that the Q is A times V, right? And of course, the A is the cross-section area. So he, again, just trying to tell us, so if you want the head of the turbine, that's what this thing is, the head of the turbine. It's delta Z that's available minus H loss. This is simply H turbine is delta Z available minus H loss. Right? And what is H loss? The K, the friction factor, okay, and basically a bunch of losses that is there. And eventually he's saying that the power, what is rho Q? That's M dot, right? M dot multiplied by GH. That work T thing is simply GH. Okay, so again, kilogram, joule per kilogram, multiplied by kilogram per second. You get yourself your kilowatt or watt or megawatt. Question so far? And he's explaining to us how do we get the Reynolds number. So the Moody chart that we just explained, where's our Moody chart? Did we get Moody chart somewhere? That Moody chart with those curves, where F here and U is here. You can read it manually, but if you're gonna solve this using a computer, you need a formula. So fortunately, when the flow is laminar, when the Reynolds number is less than 2,300 in the flow, you have only one curve, and that curve say that F is 64 over the Reynolds. Now, for all those configuration, you should basically have a formula that have the epsilon over D and the Reynolds number. And there are a bunch of formulas that do that job, not just single one with different accuracy, and that's, he's showing us some of them. Okay, so those are all examples for different way to calculate the F. Again, for laminar flow, only one curve. Isn't that amazing? Isn't that weird? That for laminar flow, it doesn't matter what is the roughness. That is super weird, right? Like no matter whether you are rough or smooth, one friction factor. All the pipes, concrete, glass, one friction factor. Why? Because when the flow is laminar, that means that everyone is just like going in line. So you could feel that, well, people don't really go to the pipe. It's like if there is a bad place in the city and no one ever go there, the city does not care because no one go there. But if there is turbulent flow, which look like what? This is the turbulent flow. The flow go from right to top. Yes, they are all going from right to left, but in what direction? Bum, 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 bum. This is actually very good for mixing. People in industry, when they have like a mixing line, you add a bunch of chemicals together, you love turbulence. They actually introduce turbulence by putting turbulator inside the pipe. Those are like some kind of X's like this, and they put them in the pipe so that the flow hit the pipe so often. That's when the flow go to the pipe. And that's why the pipe matters. And that's why you see a formula that have the epsilon over D in it. Right? So you get the Reynolds and you get the epsilon over D. Now, when the flow is fully turbulent, what happened? When the flow is really turbulent, I don't see, look at this equation. When the flow is fully turbulent, fully rough, friction. What did we miss? We don't see the Reynolds. How does this look like on the chart? The chart, what happened to my pencil? It's really weird. Why they are not focused? Feel I'm doing something. All those curves become like this. Okay? They flatten up. So at very large Reynolds number, it doesn't matter what the Reynolds number is. What only thing that matters is epsilon over d. If your epsilon over d is this like 0.01, you get this. 0.1, you get this. 0.1, you get this. 0.0001, you get this. Here, the Reynolds number did matter. And here, only the Reynolds number matters. So Reynolds and epsilon over d, and eventually you just epsilon over d. Okay? So this is fascinating, but we'll leave this for you when you go to graduate school. You think about why, when it gets really big, it doesn't matter anymore what's the Reynolds number. It's actually very interesting from fluid mechanics point of view. Okay? But the point is, if you want to get a formula to calculate the friction in the pipe, you have those three choices. Laminar flow, turbulent in the middle, fully turbulent at the end when the curve flattens up, and only epsilon over d does matter. Okay, questions? So this example, is an example of like a Lambert analysis like this. He gave us the Q, the flow rate. So rho Q is m dot. And of course, raw water, you don't really need people to give you raw water. We know what's raw water, right? So raw water is what, 997 kilogram per meter cube? And when is it like 1,000? When raw is water is 1,000. 4 degrees Celsius, excellent. Only at 4 degrees Celsius is only at 4 degrees Celsius become 1,000. So he gave us the Q and he said, I have a bunch of minor loss. I have K here, K over there, and I have a, what is the C? So sometime actually they express the losses in the pipe in really weird way. So for example, what is? They can express, of course, the pipe in lengths. Like you tell you have 4 feet of pipe or 40 feet of pipe. But even the elbow or the valve or all those minor loss can be expressed in L equivalent. So what is L equivalent or the equivalent length? They will tell you that valve is as if you made the pipe 1 foot longer. The losses in that pipe, it's as if you got extra lengths of the pipe. So that's really nice because then H loss become just sigma F L over D square over 2G, where that L total is basically all the pipe plus all the fittings in equivalent lengths. Okay, and in our book also, in this formula that he showed us, they can express it in that weird way that the loss coefficient, he can give you K and you add it to the FL over D, or he can give you C so that you can multiply by F turbulent. So it's different way to give you a loss characterization that is really correct. So sometimes they can correlate with the velocity, and that's the K, and sometimes they correlate with the F turbulence, which is function of, again, epsilon over D and the Reynolds number. So they are basically telling you our fitting doesn't always have the same K. It changes with the Reynolds number. So what's the best way to do this? relate this to the friction factor. Like we are twice the friction factor. Find your Reynolds number, epsilon over d, whatever your friction factor is, our C is 2, multiplied by 2, or 0.5, or 0.1. So when I was undergrad, my senior design project was designing a big crude oil pipeline that go from one sea, Red Sea, to the Mediterranean. And we spent like almost 2 months accumulating all those friction factor for different valves so that we can make a database that our program, we made a program that can actually design the pipeline by itself. But we needed all the fittings for all the valve and elbow and stuff. So you collect those things and you can see amazing discrepancy, not discrepancy, but different way that people characterize the pressure loss in their fittings. Okay, so don't be annoyed. It just happened. That sometimes they give you K, sometimes they give you C, sometimes they give you the equivalent lengths. Okay. So determine the power in kilowatt that can be expected from the facility. So we should get the power in watt, and then at the end, divide over 1,000 for him. So stick to SI. Okay. And he said, show that the type of the turbine to be installed is a Francis turbine, if the desired rotational speed of this. We will see next how we can pick the right turbine, because there are different turbines that we can use. Okay. But this part, we explain how to solve the first part, right? All you have to do is use the equation and add the losses, and they will tell you how much is available for the turbine. Make sure, makes sense, right? And then once I get H turbine, I multiply by G, that become my GH, that become my joule per kilogram, and then I multiply this by how much to get M dot, to get the power? M dot. Power is M dot multiplied by GH turbine. Okay, and H turbine is the head available minus the head loss, right? Minus V square over 2. And sometimes he give you the V2 at the exit, and sometimes he tell you determine the maximum possible head that we can, or the maximum possible power. Well, the maximum possible power is V equals 0. V2 is 0. Is that true? No, it's never going to be 0. Huh? Why it's never going to be 0? Because what? Why V2 is never going to be 0? Because the water need to leave, right? I mean, even if you make this pipe draft tube as infinity, means that you are never really going to get to infinity, because the river is not infinitely deep. But yeah, it's so. But you would say for maximum possible ever. It's like when you try to calculate the efficiency of a cycle, you say, well, assume the Carnot cycle. Are you really going to get the Carnot cycle? No, you're not. But why you're using it? You are using it as a ceiling of your dream. It's like you're basically trying to figure out when I'm going to buy my house. Well, assume the maximum saving. What's the maximum saving? Your income. That's the maximum saving. Let's see how many years I'm going to get to buy a car or buy a house. Are you really going to save all your income? No, because I still need to eat and drink and buy clothes and pay the cell phone. And but going to this ideal scenario, say, well, let's get the maximum possible. Just tell you, well, based on this income, you're going to get your house in 300 years. Okay, it's not going to happen. Let's forget about it. Or using this ideal scenario, you're going to get it in 5 years. Okay, that makes sense. 5 years, and this is ideal scenario. Maybe my efficiency will be only 50%. I'm going to only save 50%. So you will fix the idealization by using some kind of a correction factor, factor of safety or efficiency. Right? Very good. So now what are the kind of turbine that we can use? There are basically 3 kinds. The main kinds are axial turbine, and radial turbine, and something in the middle that's called mixed. Okay, what are those? Those are based on the direction of the flow with respect to the x of the machine, the x of rotation. So an axial machine, if this is a rotor, look at my hand. If this is a rotor and the flow come like this, and he leave like this, but it's still in the plane of the x, this is axial machine. That's like wind turbine, right? The flow come like this, yes, he leave with a twist, but still in the x direction. That's axial machine. Okay, radial machine. So that's axial machine like this guy. So notice how the flow at the inlet of the rotor is axial. At the exit of the rotor is axial. Yes, he comes with a twist and he leaves straight, but still in the axial direction. And notice how this tube over here around that actually spin around him like this. The flow coming to that root, that stator, is actually in the radial direction. But as far as the runner itself is concerned, the flow came axial and leave axial. So it's not the whole machine, it's just the rotor. How does the flow approach the rotor? So I'm basically trying to tell you that forget about this inlet and this inlet. Just look here and here. He come axial and leave axial. That's called axial machine. The radial would be this. This is called Francis turbine. So those are the rotor plates. Okay. Obviously, the flow has to leave in the axial direction because he's just leaving with the pipe. But when he come in the rotor, look at this. He come in the radial direction. So that's radial machine. And he could come a little bit with an angle like this. So that become mixed, not pure radial and not pure axial. So that's a mixed machine. And what is those yellow plates over here? You see them? What are those yellow plates? Those are, actually it's red plates. What are those? Those are the stator. See, the flow come in this pipe and he enter, you want to enter radially. But rather than letting him enter radially like the bus stop or something, you want to twist him before you go onto the rotor. So the stator twists the flow, right? And the rotor take that twisted flow, turn him, use it to turn, and let the flow leave axial. Very good. And of course, that shaft, with a big bearing here to hold it steady, have the generator on top of it, which will give you the electricity. And that built-in wheel is a little bit different. We call it impulse turbine. That's a really weird name, and it means it's not like pulsing or anything, but it's really it means that the rotor is open to the atmosphere. So what does that mean? It means that when we shoot the water on that rotor, the water is already flying in the air. So when the water is flying in the air, the pressure as it hit the plate and drop from the plate, it remains atmospheric. The pressure is constant through the rotor. Okay? As opposed to what? As opposed to those machines. So in here, actually in those machines, the pressure could drop or change. I mean, it has to drop because we build the pressure because of the high elevation. The pressure drop in the rotor. Okay? So we're here, where does the pressure drop? First of all, why the pressure is building up? Because the water is dropping, say 100 meter or 60 meter or whatever. By the time it hit this point, what is the pressure here? Maximum, like what's the ideal pressure? Assuming no losses in the pipe. Ideal pressure would be, rho G H. If he's not moving, if there is nothing converted kinetic energy, all the H that you have on top of you, the hydrostatic pressure, basically, that's the rho GH. Right? You have this liquid on top of you, the pressure at the bottom will be rho GH. Right? That's why, what is the pressure in this room right now? 100,000 Pascal. Where did this come from? Rho GH. What is rho GH? Rho air, which is 1.2, let's call it 1. H, which is 9.8, let's call it 10. And H, which has to be 10,000. So the 10,000 meter of air on top of my head, multiplied by the G, which is 10, multiplied by rho, which is 1. That's how I get my 100,000 Pascal on top of my head. Right? And if you go to the swimming pool, which is like, and you go, you only need what to get 2 bar? You just need 10 meters. Right? If you have 10 meters of water on top of your head, you can get 1 extra bar. Because raw water is 1,000, G is like 10, and H is 10. Right? So you can get the 100,000 from 10 kilometers of air on top of your head or 10 meters of water. Right? So if the dam is 10 meters, the pressure is 2 bar at the bottom. Make sense? So all that pressure over here will get converted into V. All that pressure will get converted into V through the nozzle. And that very high velocity will end up hitting the impeller. Okay, so again, that's an impulse turbine, where all the pressure drop happen in the nozzle, which is considered the stator here. This is the fixed part. And the rotor itself, he's running at the same pressure, atmospheric pressure. So that's what we call impulse turbine. That's the same thing in steam power plant too. You can design a steam turbine, not hydraulic turbine, a steam turbine, where the pressure drop happen only in the stator, and that's called an impulse turbine. Or you can make one where the pressure drop on the stator and on the rotor. And that will be called, the opposite of impulse turbine is, what's the opposite of impulse turbine? So impulse turbine versus reaction turbine. Okay, and what is a reaction turbine? It's a one that have a little bit pressure drop on the stator and the rotor. Okay, and so is it 50-50 or 70-30? This is called the degree of reaction. How much pressure drop happen on the stator and how much pressure drop happen on the rotor. Okay, and if I draw the stator and the rotor of a turbine, you will see that this is not good. You will see the plates. It's hard to draw those guys. You will see how the stator get the velocity like this and they leave like this. And so what I'm trying to plot here is to show you how A1 and A2 is different because of this angle. So what happened when you send the flow into a passage jet getting smaller and smaller like this? That's called a nozzle, right? When you leave at very small area, what happened to your velocity? and the pressure, and that is the idea of the stator. Yes, we want to spin. I kept telling you about spinning, but also not just let him spin, but also accelerate him. We need to let him, we need the flow need to leave the stator at very high velocity. Yes, with a twist, but also with very high velocity. That's why the pressure between V1 and V2 will drop in the stator. Okay, now if the impulse turbine, or if the turbine is impulse, we will actually make the plate like this, and the other one also like this. And what I'm trying to plot here is I'm trying to show you how the inlet area here is the same as the exit area here. So W1 and W2 on the rotor, if you see them having the same exit area, like the inlet area, you tell yourself, well, he did not accelerate in the rotor. That must be an impulse turbine. That must be a turbine when the pressure drop doesn't happen on the rotor, only on the stator. That's an impulse turbine. But if the rotor plate actually, if the rotor plates are such that you actually accelerate the flow, and how do you do this? Well, you need to make sure that the area is smaller on both sides too. So it's smaller at the exit. So the flow, this is not a good one. If I can just copy it, it would be perfect. So I'm trying to make W1 coming in a bigger area than W2. So you see a rotor like this, and you tell yourself, wow, look at this inlet area, and look at this smaller exit area. Especially if the plate is like really big, so that it's like a little bit full. So this would be a reaction turbine, okay? Because the flow will accelerate as he goes through the rotor too, the moving part. So the stator shoot the flow, he shoot it with what velocity? V1. And V1 plus U1, sorry, U1 plus W1 make the V1. See, I'm trying to make V1 different from W1 by difference between them is U1. Okay, so he get W1 like this over here, and he turn around and pushing the plate here. And by the way, in an axial machine, U2 is the same as U1. Unlike radial machine, that U1 is different from U2. In axial machine, U2 is the same as U1. Okay? Anyway, when you look at the stator and you look at that rotor, you feel as if they have the same geometry, just that, or the same area reduction on them. This guy's this way, this guy's that way. So when you see the symmetry between them, if they are the same angle almost, but the other way, that's a 50-50. But you see one of them that is only the stator have area reduction and the rotor is doing nothing for the area, that's an impulse turbine. Okay? Make sense? All right, so when we, I want to say one more thing about this turbine plate. So which one you think have higher flow rate or can handle higher flow rate? The axial machines or the radial machines? And the one that will handle higher flow rate usually does not have that much pressure drop on it. So those are opposite to each other. Like if you really want to build very high pressure, you will have to be happy with lower flow rate and vice versa. So which one do you think will handle higher pressure drop? The radial machine. Radial machine can have huge pressure drop because you can see how they have like tight passages. You can really control the pressure. But this guy is like it's open, almost open. So you handle a lot of flow rate in it. And that's the same for the jet engine too. Like axial compressors can have huge flow rate but small pressure drop. That's why you see so many stages because each stage have a little bit pressure drop, a little bit pressure drop. But radial compressor, they have huge pressure drop or pressure increase across them, but very small flow rate. All right. So this graph is showing you how much power one should expect. This is the power in megawatt. So that means 1,000 megawatt, that's 1 gigawatt. One turbine, one runner can give you 1 gigawatt. Okay? How is that possible? Because the power is m dot gh. And what's m dot? That is rho multiplied by q. And raw water is 1,000. So you already got 1,000 sitting over there. So even with 1 meter cube per second, that's already 1,000. And you got yourself 10 over here. So it's super easy to like 100 meter. 100 times 10, that's 1,000 times 1,000, that's 1 gigawatt, right? If it's 10 meter, 10 times 10 times 1,000, right? It's 10 meter. Very good. So they are building bigger and bigger. You can see how China is building bigger and bigger dams. And there are, you would think that all the dams has been built in the world. No, there's a lot of places that's untapped, a lot of hydraulic power, especially in Africa and China, that's basically available for hydropower. For example, Iceland, as I told you, they extract all their power for the whole country from hydropower and geothermal energy. Okay, so it can be huge. All right, and you can see the size of one of those turbines. See that the people, how small the people are compared to the runner. Okay, very good. So we have radial machine where the flow come like this and leave. This is for a pump, and if it was a turbine, it will come like this and go that way. And you got yourself axial machine. This is the plate, right? So the flow come here and leave here. So those are axial and those are radial. And the question, those are pumps, and those are turbine. And what is the x-axis? It's how we characterize those impellers, something called the specific speed. So for axial machine, that number would be this much. For radial machine, it would be this much. And we will see how we can use this to pick the right type for us after the break. So take a 12 minutes break or something, and we'll come again at 9 o'clock. That's a very good question. And the answer is Andrew is currently the TE, but Andrew is probably gonna switch to research assistant next week because we got a new fund to do some research for him, and so we're gonna have another TE. But currently Andrew is the TE, but it's probably gonna take a week or two. So the fund was just approved uh, actually today, and but it will take time to get the paperwork. It's actually get the number, account number, and then hire him as an RE. All this paperwork is gonna take maybe a week or something. So if you need help with the homework, you can ask him now, or you can ask me, which will be faster. No, it's master. Mhm. Right. I think we should start again. So, people online, can you hear me?
Yes.
All right. So, we said we have different kind of machine, axial, radial, and the question is which one we should pick. Like say you are designing the dam for Keystone over here, and they tell you which turbine you should pick. What should you do? And so you should ask about the G, sorry, not the G. We know the G, right? It's the H. We should ask about the H, and you should ask about the Q, the flow rate that they want to send through, and the head that we're gonna build. Now, those two numbers, huh? Those two numbers, the G and the H, are the basis to come up with this x-axis. Okay, there's something called the specific speed. Okay, for pumps and for turbine. Okay, so the specific speed has actually two ways to do it. To calculate, it's the same formula. Not that. Let's look for the pump, for example. This one and this one. It's the same formula except the one downstairs does not have G in it. And also omega is in RPM. Okay. And the Q is gallon per minute and the H is in feet. So this is actually, those units are very convenient for us, huh? Because RPM makes sense. People will understand the RPM and the head in feet and the Q in gallon per minute, although that's not the right way to use it. If we're gonna use SI, we don't calculate Q in gallon per minute, right? What do we use for Q? For SI, if we wanna be kosher, you know, what number unit we should use for the Q? Meter cube per second, and in SI we should use feet cube, right, per second in English unit. But gallon per minute is so convenient, huh? The same thing for omega. We shouldn't use RPM, we should use radian per second. So when you do this, that's what we do in the USA because it's very convenient for us. We calculate the specific speed with omega RPM, the Q is in gallon per minute, the H is in head, and for the turbine we use W, which is in horsepower. Again, very convenient. So that specific speed that we calculate, or the specific speed prime, is not dimensionless. It has units, and actually it has a really weird combination of units because of all that mix. The SI version is basically this. You can see how in order to make it SI, you actually have G in it, and he will tell you have to use exactly the right units for it. So what's the consequence of this? The consequence of this is that there are two scales, okay? One that with the unit that we love, and the other one that is dimensionless, okay? So make sure that you use the right scale for the right formula, okay? So fortunately, they tell you that's in prime. So you know that this is the one that we actually have the convenient unit with. Okay, so I calculate this for Keystone Dam, and it's like 1,000 or 100, 300. What does that mean? If my specific speed is 100, it means that if you buy an axial machine, a Kaplan turbine, your efficiency is expected to be this. And if you say, no, I'm going to buy a Francis turbine, you're going to use this. So this basically tells you that the Kaplan is much better for this range. The Francis, which is kind of radial, is better for that space. And the impulse is better at that range. So that's how you can make your decision. So sometimes people use, I mean, if you are here, Huh? It doesn't really matter that much. And then you can use the cheapest one. Yes. Yes, excellent. Excellent. This is 80. Yes. 70, 80, 90, and 100. Yes. So some problem he will basically tell you pick the right, like the example that we saw. What is the right machine that we should use? Well, you calculate the specific speed. You come over here and you see basically which one is highest. Okay. And based on that formula, for the specific speed, you see how that as the head get bigger and bigger, which one we should use? When the head is higher and higher, you should go toward what do you think? For a very high head, you should use what? Impulse or Kaplan? Very high head mean the specific speed is going to be small or big? Small, right? And small, that means that you move to this. Very small head, it moved to this. Does this make sense? Yes, because we said the Kaplan as an axial machine, it cannot have that much pressure head on it, right? Because the rotor is like really open. So small head, usually large flow rate, so that you can get some power. I mean, if you only have 10 meter, how you can make this pay for itself? You need to send a lot of flow rate. And for very big head, when you think about it, how could this guy handle large flow rate? It's usually very small flow rate, because it's just like a bunch of buckets. So very large head, use impulse. Very small head, use axial. Okay. Large head means that the dam is very, very high. And so the GH would be really big. And therefore the pressure in the just before the stator is really going to be really big. And so that's why you need something confined to handle that pressure. You will not be able to handle huge pressure with an open rotor. You need closed rotor. Right? And you don't really need to think about it thanks to this chart. This chart make it, kind of even like a very easy task to do. You just calculate the circuit speed. Where are you? You come here and say, look at this. Kaplan would give me this efficiency. Francis will give me this. Of course, I'm going to use Francis. If my specific speed end up being like this, like 15 or something, which one I should use? An impulse or Francis? Yeah. And of course here, if it's 10, you can choose. Both are the same. Maybe you find the cheapest. Make sense? And the same thing for the turbine, for the pump, by the way. So all those, remember the hydro storage system that I told you, where you have a turbine and a pump on the same shaft, and when you have extra power, the pump work and take the water to the dam or the lake, and when you need work, you run the water the other way in the pipe and the turbine work. So you can make the pump the same way. You can calculate the specific speed for the pump, and you go to that chart for the pumps, and you basically tell yourself which pump I should use. Pump specific speed relation. Okay. And you'll be able to pick the right kind of pump as well. Okay. This is actually the chart I wanted, the figure I wanted to show you. I love this one because they made the cover out of plexiglass so that we can see. You see that this is actually supposed to be metal, but you can see how the flow come. And first of all, look at this. You see how the inlet area and the exit area, inlet area and exit area, what does that look like? A nozzle, with bigger inlet area and smaller exit area. So the flow shoots, at very high velocity over here. And also that this and this, that is the direction of V1, right? This is the direction of V1. The velocity, maybe back. V1 will come like this, and you can divide V1 into V1 radial component and V1 tangential component. That's the V theta 1. That's the one that we care about. Exactly. But let's not call it theta, let's call it alpha, because the angle that V1 is making with the tangential direction is called alpha. So if this is V1, the tangential component is V1 cosine alpha, and the vertical one is V1 sine alpha. Yes. Okay. So those are the equations that we wrote, right? And he, over here, he's basically making the point that when you calculate this equation, depending on which one is bigger, you can end up with negative power. Okay? And he's actually saying that in the case of the turbine, you will end up with negative. How is that possible? Because he's saying that the torque and omega, the torque and the rotation should be negative or against each other in the case of the turbine. Okay? Think of as a fluid. Think of yourself as a fluid in a minute here. You are fluid and you're going into a pump. How do you feel when you're going through the pump? You feel the plate behind your back is doing what? Pushing you forward, right? The pump push the fluid. So as a fluid going into a pump, I feel the torque is like, get out, and like he's kicking me. But if I'm fluid going into a turbine, and the shaft of the turbine is connected to what? In a turbine, the shaft is connected to a motor or a generator. The shaft is connected to a generator, right? That generator is very hard to move. Why? Because when you spin him against the electric field, he makes electricity. So that generator needs something strong to push him. So as a fluid go into a turbine, I feel that the plate is not actually moving. And I have to push him so that I can come out. It's like, get out of my way, let me leave. So the torque in a turbine will be resisting your motion. Huh? So the torque and the omega should be opposite each other. And for a pump, it should be the same. So how does this translate into actual number? So in actual numbers, when we draw omega in that direction, huh? And we make, say, V1 in that direction. Actually, let's make omega in the other direction. And we say this is, again, this is alpha, and this is V1 theta, and this is V1R. When we write this equation for the torque, m dot R2 V theta 2 minus R1 V theta 1, those guys have a sign. Those guys will be plus or minus, positive or negative. When you write V theta is 30, you have to tell yourself, is it 30 plus 30 or minus 30? How do you determine this? If this was just like linear motion, things are running in the, we would say, well, here is the x direction, and anything in that direction is plus. If the velocity is moving against the x, it's negative. But when things rotate, we need to define what is the correct rotation, not correct, what is the positive rotational direction. So the default is this is the positive. Why? Because right hand rule. So if I draw X and Y like this, that would be the positive momentum. Right hand rule, it needs to rotate like this. Then if there is actually a torque on that page, Z will be out of this paper. And so he needs to rotate like this. So this torque would be positive. Okay? Not because he's moving with omega. No, because I just said that this is a constant direction. But just like in linear momentum calculation, you probably have solved problem where the X or the positive direction is not in this way, but the other way. And the problem should have said, should got exactly the same answer. Like I'm talking about those momentum equation where you calculate the thrust of a jet engine, or how much force does it take to hold the pipe in place. Your professor probably have told you, whether we assume this is the plus direction or this is the plus direction, we should still get the same answer. So same thing over here. What I'm saying is that if you screwed up and decided that, you know what, the positive direction is going to be this way, nothing bad will happen if everything is following that rule. So you basically say, are you moving in that direction? Then you're plus. If you're moving against, it's negative, and you will still get the same answer. But I just think maybe it's wise and a good practice to stick to the counterclockwise direction. Okay. But don't panic if you see someone choosing the positive direction to be the clockwise, not the counterclockwise. So what I'm saying is I'm gonna use counterclockwise as my positive direction, and I'm gonna stick to it. And so if I see a torque like this, then it's gonna be plus. Of course, we are not seeing a torque, we are calculating a torque. So I'm saying let's calculate the torque, and when the torque ends up being plus 30 Newton meter, we would know it's plus, it must be counterclockwise. And if that calculation ends up being minus 30, then we know that he's actually clockwise because he ends up being minus. And when it comes to V theta 1 and V theta 2, we need to see, are they rotating clockwise or counterclockwise? So in this example, let's say V1 theta is 30 or like 10 or something, 10 meters per second. Should this be added as plus or minus? Look at V1. It's moving in the, so it's going to be plus, right? And the same thing for the U1, in case you want to calculate U1. Baby, you had a question.
Yeah, over here, where is theta in that field?
So X and Y. This is Cartesian coordinates, right? And if I tell you this point over here has a coordinates of 3 and 4, what is the 3 and what's the 4? The 3 is the X, this is 3, and the Y is the 4, right? Well, we can also make that point instead of 3 and 4 by R and theta. What is theta? Theta is 10 minus 1, 4 over 3. And what's R? The square root of 4 square plus 3 square, right? So theta here mean the tangential direction. It's the coordinate system. So rather than telling you, this is my Vx and my Vy, I call it Vr and V theta.
So basically, it's a slope.
Theta is the angle of the vector.
I mean, 10 theta is the slope.
10 theta is the slope of what? Of that point connecting this. But when we say Vr, I just want you to realize that that V1 is not just here. That V1 is also here, and here, and here, and here. So if I try to explain that velocity vector by x and y, I will go crazy. Because what is v1x and v1y? Like which one of them? Each one of them, like the vx and vy will be different. But if I describe that velocity field by vr and v theta, it's going to be the same everywhere. So that's why they use the polar coordinate system for turbo machines. And that's why the equation is written like this. Okay?
So, okay, if I understood correctly, in that figure, where you mark that alpha, right?
Mm-hmm.
That's the angle meant by the velocity, right?
Yes.
V1
Yes.
in the x-axis.
With the tangential direction.
Tangential line.
With the tangential direction, because v1 over here is not going to make it with the x-axis.
Yeah.
It's going to make alpha also here, right?
So that v1 theta will be v plus alpha.
Yes, v1 cosine alpha, correct. v1 theta is going to be v1.
Cosine alpha.
Yes,
And that v1 r will be the
sine alpha. Of course. Yes. Yes, correct.
okay, now I am.
Yep. Very good. Okay. So I wanna solve an example. I wanna show you. You have to approve. What happened? In the old time, people just used to log in. And now I have to approve. Old time on 2 machines. Okay. So when you go to the homework section, so this semester I'm teaching 4263 with energy conversion and 5263, which is a graduate course of this. It's called combustion. So interestingly, or like 263, 4263 and 5263. So this homework example, obviously, this is already solved for us. Okay, so you don't actually have to solve it again. But I'm just going to show you what is the format that I would like you to solve the problem with. So here is the problem. Okay, so it's a pump. How could I tell it's a pump? Just by this drawing, without even reading. Looking at this, you can tell this is a pump, not a turbine. Why? Look at the rotational direction. The rotor, whatever this is a turbine or a pump, the rotor is rotating clockwise. And the flow coming in, this is V1, is coming all axial. And he's leaving with, this is V2 theta, right? And this guy is V2R, correct? Make sense? This would be alpha, by the way. The angle that V2 is making with the tangential direction. So how did I tell this is a pump? Because in the case of a pump, the impeller spin the fluid. The impeller give the fluid rotation. Huh? He come axial and the fluid rotate him. And that's what happened. He come all axial and he's leaving with a clockwise or negative in our direction, a clockwise spinning from the omega. Has this been a turbine? He should have left with the opposite direction. Like he would kick the impeller in the back and went the other way. But because the impeller is spinning the fluid, it's a pump. Okay. And this is funny because you should think, so people build pumps to spin fluid? No, they build pump to increase. What's the job of a pump? What's the job of a pump? Why would we buy a pump? Increase pressure. But again, as I kept saying all today and last week, that what happened really in the impeller is just spinning. Okay? So he gave him V2 theta, but then that's leaving the impeller. Then what is outside the impeller? The stator. How does the stator of a pump look like? This volute casing. So the fluid come here and he find bigger and bigger area. He slow down, and slow down. And he slow down, he build his pressure. You slow him down, his pressure build up. So the rotor give him angular momentum, and then the fluid move with this angular momentum and slow down and build the pressure. Make sense? So the immediate action is exchange of angular momentum, but this translates into pressure later on. Okay, so he's giving us the omega, but in RPM. And he's giving us the velocity at the exit, V2, and the angle. And he said calculate the torque. So I always say in my courses that understanding the solution is super easy. Right? I mean, once you see the equation, you see the number, that is the easiest part, especially if I explain it well, and especially if you are following me, they will not have any problem understanding the solution. But that's not really what's important. What's important is to come up with the solution yourself. So after you read any problem, or we go through every problem, don't just tell yourself, did I get it? And it's not, did I get the solution? Did I get the solution strategy? If I start this problem from scratch, would I think that way or not? Because that's what you will take from this to different problem and actual life. Not this particular problem. That's why when people copy homework, they don't really learn. Because just reading the English and figure out, well, he used this equation, he put the number, so what? But why did he use this equation? Was there any other equation? When would I touch this equation and when I not? Right? So that's what you need to get. So I always ask yourself, and if you don't get, so if I just say torque is m dot r2 v theta 2 minus r1 v theta 1, and start pulling the number, you will understand the equation because we have been talking about it all day long, right? But what you need to ask yourself is, why did he pull that equation? And when I will not be able to pull this equation, for example. So why did I pull this equation? Because he said calculate the torque. Yes, that's a good reason. But also because what we see in front of ourselves is fluid coming straight and leaving with an angle. And so in front of our eyes, the phenomenon in front of our eyes is angular momentum being exchanged. And he's asking for the torque. So what then you need to get into your mind is, what is the relation between the torque and the angular momentum? Then you will build this equation, because that equation relates the two of them. Has this problem been, the pump has this pressure, calculate the torque. I'm not going to build this equation. I need to find what control the pressure. Right? Maybe the power of the pump. Maybe I need to, that thing that he said at the beginning of the lecture, when he said if you put a control volume, Bernoulli equation will be able to give you the head of the pump as function of the pressure at the inlet and the exit and the velocity. So always question not the understanding of the equation, but why did we use this equation in the first place? Okay, so this makes sense because we see spinning and he's asking about the torque, and that is the relation. So every equation, I always say, can only give you one unknown. So if he is after the torque, we need to know everything else. We need to get m dot, we need to get v theta 2, v theta 1, that's very easy. R1 and R2, that's also very easy, right? I guess the only thing that's a little bit hard is m dot. How do I get m dot again? What's m dot? Huh? You said it before. What's m dot? Rho A V. Rho water. The question is what A and what V? So by the way, what's the relation between m dot 1 and m dot 2? Are they different? Same? Same. Otherwise, the bomb will explode in a few minutes, right? It has to be the same. And so we can do A1 V1 or A2 V2. So again, I can just write the solution and say rho A2 V2, but you need to ask yourself, why did he use the 2, not the 1? Why will I use area 2 V2, not area 1 V1? Because I don't know 1. He didn't give me the area, the velocity at 1. I actually even don't know the area at 1. I don't know the impeller inlet. I don't know the V1. So why would I use it? It's easier to calculate from the side that I know. Say that again. They are the same. M dot, whether you're going to say rho A1 V1 or rho A2 V2, it's the same. Okay? It's the same flow. That's why I asked you guys, what's the relation between m dot 1 and m dot 2? Between the inlet and the exit. And you guys said it's the same. If 1 kilogram per second come, 1 kilogram per second need to leave. Or, no, if we know area 1 and V1, I will calculate m dot from area 1 V1. Why wouldn't I calculate it from m dot 1? The mass flow rate from 1 or 2 should come to be exactly the same. Of course, because what? Because it's kilogram per second. The mass is conserved. What does it mean that the mass is conserved? It means that if you think about the fluid as billiard ball. The moment you squeeze a billiard ball in, a billiard ball will have to pop up from the outside, from the other side, because there is no space. So not only m dot equal m dot, it's the flow rate is the same too. Sorry, the volumetric flow rate is the same. Q1 is the same as Q2, right? And you know, I'm never ashamed to say that this simple fact, I screwed this up in my first undergraduate fluid mechanics. I still remember that problem till now. I screwed up the first midterm in fluid mechanics because I didn't remember this. So how is that? So we had like a problem like this. My first midterm, that was in 1991 or 1990 or something. And he said there is this fluid rho and this fluid rho 2, and they mix. And so he gave us area 1 and V1, and he gave us area 2 and V2, right? And he was asking about the V3 over here. Okay, and he gave us area 3. So the question is, what is the velocity at the exit? And so you are not really sure what is rho 3. Huh? But so it's not just m dot 1 plus m dot 2 equal m dot 3, because that is correct, yes. But that leave you with rho 1, V1, area 1, plus rho 2 area 2 V2 equal rho 3 area 3 plus V3. And rho 3, you don't know rho 3. And so there's two unknown. But because the flow is incompressible, why it's incompressible? Because it's liquid. Because liquid, you cannot squeeze them. Imagine if your fluid, the brake fluid in your car is compressible, you push the brake, and he's like, no, I'm not gonna push the brake. I'm gonna squeeze, and you're not gonna stop. Fortunately, it is incompressible. So the moment you step on the brake, it also go to the wheel and stop. So because of this, Q1 plus Q2 equal Q3. So area 1 V1 plus area 2 V2 equal area 3 V3. So my heart was crushed some, I don't know, how many years ago is that? 30 years ago. My heart was crushed because of this, and I still remember it. So same thing over here. The flow is incompressible. Area, besides it's the same rho too. All right. So let's do it from the two direction, because that's what we got. I mean, that's the velocity that we have. Right? So I'm gonna do it from the area 2. So here is the question. What is the area 2? Can someone help me? So that impeller is opening like this, and then there is a strip on the outside that he leave from. It's a cylinder, so it's 2 by R2H, where this is H. Okay, and if I step here a few slides, that's how it will look like. Let me rotate. So look at this. This is area 1 V1, and then when he leave like this. Is that an axial machine or radial machine? Help, axial or radial, guys? Radial machine, excellent. And this is the H2. And if you are after the area 2, what's the area 2? It's this strip, right? Or in this case, it's this guy. This is all the area 2 of the radial machine. So 2 by R2 H2, right? And now what velocity should I multiply this area with? Should I multiply it by V2 or V2 theta or V2R? No. No. So what's the answer? V2R. So why? What did I say last week? When it comes to m dot, and we say rho AV, that V need to be, what is that symbol I'm trying to plot? Normal. V normal. The V need always to be normal to the area. The V need always to be normal to the area. So V2R is normal to the area. V2 theta is parallel to the area. So the one that will actually leave with is, or cause the actual flow rate to come out, is V2R. Make sense? Yes? Okay. So then those are the two equations, that we use to calculate the two. Turbine or pump, you use the velocity normal to the area. So you need to tell yourself which velocity is normal to my exit area. And it's not going to be the tangential. No. The tangential give you the torque, but the radial for a radial machine or the axial component for an axial machine are the one that actually make the flow rate. that actually make the m dot. The tangential component make the spin, and the axial component is the one actually making the actual exiting. Okay? So those are the two equations, huh? But I'm showing this example because I want you to write the solution like this. Okay? There are 4 points in your homework associated with that structure. When you say what's given, what's required, and the solution, and you make a nice sketch of the problem, you get your 4 points for what we call identify. You identify the problem right. You said what's given, and look at what I'm doing over here. You see this? So that given section is for that, is to fix your unit so that you don't mess it up later on. Whatever he tell you in the problem, you convert here before you go any further in. Look at this too, the rope. I didn't want to do it in pound mass. I stick to a slug per feet, Q. All right? And you tell yourself, you know, what is required. And actually, I think it's really good practice when you write what is required to even write the unit. Because sometimes he would tell you calculate the power in horsepower. So you may want to tell yourself he want the power in horsepower between brackets, so that you remind yourself that yes, you want to calculate it in SI, we're going to calculate it in watt, but then in the last line in the problem, we're going to switch to whatever he wants. Huh? So here, I guess he said it's going to be feet pound because it's English unit. So you can remind yourself. Feet pound, and you just put it between brackets like this. Okay, so 4 points for, and actually this is worth 30% of your final grade. And then 4 points for the solution, which is what? This equation and the equation for m dot, which is actually over here. So that's also 4 points, which will be 40%. And then this final answer is worth 30%. Again, you get 4 points over it. So you get 3 grades of the homework problem. You'll get 444 or 432 or 431. And then we will add them together with those percentage to get your actual grade. Does this make sense? Now, interesting, look at so he put the equation, torque is m dot R2 V2 minus R1 V theta 1, and he see the flow is coming in axial. So V theta 1 is 0, right? And he's looking at m dot, here's the m dot, and then V theta 2. And he write V theta 2 as minus V2 sine 30 degree. Why minus? Why V theta 2? Why this guy was considered minus? Yeah, because we said that is the positive direction. It does help to remind yourself that when things are moving in clockwise, counterclockwise is positive. So that's why it become negative, okay? And so then the torque, when you calculate at the end, the torque become negative because of the sign of V theta 2. So when the torque is negative, what does it mean? What direction is moving in? Clockwise, just like the omega. So then are we happy, or does this make sense, or no, it does not? A pump and the torque is moving with omega. Does this make sense? Totally makes sense. We said in a pump, the torque is behind you, is in your back, he's pushing you. So the torque and omega should be the same for a pump. The torque and omega should be opposite to each other for a turbine. Because what I said, the torque is resisting the motion. Right? So the fluid is turning the turbine, but the torque is like, no, no, you cannot go. And like, no, move, move, move. And the fluid is pushing him. So in some problem, we ask you, is this a turbine or a pump? You can just calculate the torque. And if you find out that the torque and omega are opposite to each other, you can tell yourself it's a turbine. When you calculate the torque and find the torque and the omega are together, you tell yourself that must be a pump, right? And later you will be able to get that experience of basically looking at the change of angular momentum in front of your eyes and be able to say, yes, it's a pump because we just spin it in our direction. So it's a pump, right? Make sense? So there is a very clear way to determine it's a pump or a turbine. Just calculate the torque, look at the sign, and is it the same like the omega or different? You would know. Okay, but the other way to tell yourself is, did we spin him in our direction or did he end up being spun in the opposite direction? That tell you, did we give him or did he give us angular momentum? Okay, and so I would like you, since this is submitted electronically, if you find picture, that will make the things clear for you, add them. All right, so don't just finish with the solution. You can add things because those homeworks are going to be useful for the midterm. So you want to give yourself, and they will be available to you because remember the exam are open, everything. So if you have your homework with like big sketch, nice sketches and figure later on, you will be, before the revision for the midterm and the final, you'll be like, oh yeah, look at this. So what I'm trying to say is that you should invest in your homework because it will pay off. Okay. So also I want to show you, this is open rotor and this is shrouded rotor. So which one you think will have the higher pressure? This guy. Because you need wall to squeeze the fluid. This one, yes, he's inside his casing, but the fluid can jump from one to the other. Right? Also, an easy way to tell whether it's a turbine or a pump is a pump go from the small diameter and leave from the outer diameter. A turbine come from the outer diameter and leave into the smaller diameter. Right? So now this is, what do you think, a pump or a turbine? Look at the omega and look what happened to V. He ended up getting spun in our rotational direction. That must be a pump. And what is that velocity? Omega W, so relative velocity, right? And you can see how U plus W equal V. And also you can see how why W is going this way, because of the plate. So this is W, relative velocity, and the angle W is making is called beta. The angle that the velocity is, the absolute velocity is making with you is alpha. Okay, and so this is amazing because it shows you that W is going backward, but V is actually going forward, right? So this impeller is a backward impeller. There is forward, there is backward, and there is radial impeller, and they have different characteristics when eventually come to the pressure. All right, and what also we can see this, how the cross-section area is getting of the volute casing. What do you see? It's getting bigger and bigger and bigger because one, you are accumulating more flow rate, right? You get room for them, and also because you want to slow them down and get the pressure to be higher, right? Very good. And for air compressor, by the way, it looked the same, huh? Except that because he's rotating at very high velocity, V1, of course, will become like this, but because of the U, W would be this way. How did I tell that W is this way? Because of that plate. When the plate look like this, I can tell myself that plate is waiting for W to be this way, right? So that show you that U must be this way. So because he's rotating in that direction, huh? Rather than seeing V coming axially, he see the velocity coming really with an angle. Make sense? And look at this guy. He received the flow rate from here and from here. And then they go like this. So those are two pumps back to back. Why do they do them like that? What do you think the advantage of having them sitting back to back? Anyone? It cancels the axial thrust. So if the flow come from this way and go that way, the impeller will feel always pushed. All that fluid coming and leaving, we will always be pushed. So the bearing, and we have a lot of companies in Tulsa that actually make pumps, big companies in Tulsa that make pumps, and companies that make just the bearings also, and the gland that will seal the water, because you don't want the liquid, and sometimes those are radioactive material or like bad chemical, you don't want them to leak in the factory. You need to build the sealing so that the fluid that you are pumping from here and here never have a chance to actually drop. Okay, so I mean those are really expensive, to the extent that the people that selling those things think that the pump is for free. You know, you're just paying for the sealing. Very good. Here's a better picture. Okay. Questions about the pumps, turbines? All right. So now this is the second homework problem is about, actually I didn't explain this was an example homework problem, but the actual homework problem, he give you, let me show it to you. Here's homework 1. And look at this. What is that? This is the turbine, and those are the stator, right? The stator shoot V1. Okay. This was actually in a midterm 1 year. So here is V1, and the angle with the tangential is alpha. Okay, this is alpha. Okay, so you should V1 like this, and this is the U. So U plus V relative equal V1. And he's asking about what this alpha is. Okay, such that what happened? So it's required to beat at 600 RPM at a charge of 4 meter cube per second. So he gave us the flow rate and the omega, and he's asking us for the angle. So the secret, or the way to think about this problem, is you have to plot that velocity diagram. And that velocity diagram have V1 coming like this with an angle alpha, but it also have U1 and V relative 1. Okay? And since he gave us m dot, we need to remember m dot is rho a VR. VR is the radial component. So, of course, the area is what we said before, 2 by RH, right? So the question is, for VR, which VR should I use? Should I use V1 R or should I use W1R? And the answer is it doesn't matter. They are the same. As we said before, the radial component of V1, here, radial component of V1 and the radial component of W1, they are the same. The only difference is between the tangential component of V1 and the tangential component of W1. And why? Because the difference between them is the U. But W1R is the same as V1R. Radial component is the same. The vertical height is the same. That velocity diagram have the same height, whether you are using V1 or W1. And this is U. So by giving you m dot, he's basically giving you V1R. And so if you know V1R, which is this, and you know this angle, you'll be able to calculate this. And if you have this and you have this, then you have V1, and you'll be able to calculate the alpha. So this problem is all about the velocity triangle and the relation between U, W, and V. I just want you to get familiar with the angle. Okay? So you do this, you'll be able to calculate V1R, that's step number 2, and then you'll be able to calculate V1 theta. And if you have V1 theta and V1R, you'll be able to calculate alpha. Alpha stand the two guys on each other. Very good. So this now this is a power equation, right? For any turbo machines, but for the Belton wheel specifically, what is the Belton wheel? It's this guy. So if we look at one of those plates, what happened? The jet come with V1 and the plate is running away at U. And what is the maximum U that you can ever dream of? You are shooting a plate at 10 meters per second water jet. How fast can that plate move? Maximum 10 meters per second. And at that moment, they are moving at the same velocity and the torque would be 0. If the plate run at the same velocity as the flow, we will never catch it. The velocity will be 0. Sorry, the torque will be 0. And the power will be 0. You don't want the blade to run. So when this will happen? If the shaft key got broken and this impeller is running without a load, yeah, he can run at that velocity, maximum speaking, theoretically speaking. But the power is 0 because there is no torque. The other extreme is someone hold the shaft so tight and the water is shooting at V, but the plate is not moving. U is 0. The torque would be maximum, right? The U would be 0, the torque would be maximum, but the power would be 0 again because the power is torque times omega. So between those two extremes, there must be an optimum velocity for the plate. Optimum velocity give you the maximum power. Okay, and that is what he's trying to do over here. He's trying to figure out what is the maximum power. So he starts with that equation, the equation for all turbo machine. Power is m dot U2 V theta 2 minus U1 V theta 1, right? Except that he called his VU instead of V theta. But this equation is what we know. And then he tried to figure out what is the maximum power by differentiating the power. Anytime you have a relation between a variable and something else, and you want to get what's the maximum or the minimum, you do this. You say d power by d, the factor that playing with it, du, equal to 0. And so he figured out that rather than using the general equation, the maximum power can be achieved when U is, surprise, surprise, V1 over 2. So not maximum V1 and not 0. So if you make the plate move with half the velocity of the jet, you get the maximum power. And this is the maximum power. What did he do? He just substituted U equal V1 and he wrote the equation again. Does this make sense? So in the homework then, in the homework. He got those built-in wheel with 4 jets, each one of them is shooting, okay? And he's saying, calculate the maximum power. What is the maximum power when U is V1 over 2, right? And I mean, you don't have to prove it. You can just basically go to our textbook and say, you know, I know from this analysis that this is what you get. This is the maximum power. So m dot V1 square over 4, 1 minus cosine beta over 2. Make sense? And so what is beta? Beta is the angle of the relative velocity. So when V1 come like this and he leave like this, that would be your beta, because this is W2. You understand how the jet come and he bend and he leave? So the angle that he's leaving with, that's the beta, because that's the relative velocity. So you substitute beta 2, and always people get confused with this problem because they say, what is the m dot? Should I use m dot of 1 jet, or should I use m dot of 4 jets? What should I do? Yeah, because there are 4 of them, right? Yes. So why is confusing? Because you would think, so first of all, why this is beta, not alpha? Because this is the velocity that he make with the moving plate. In real life, he actually could have different V. He would leave with different V. But with someone sitting on that wheel and turning around, he will see the jet coming at 0 and leaving at 135. That is the W2, the relative velocity. The absolute velocity is different. Add the U to it, and you'll be able to get the V, the absolute velocity. Does this make sense? Yes? Okay. So I want to recap by saying that there is this power for any turbo machine. This is the equation that we use. But specifically for the built-in wheel optimized, you will use this for Bmax. Optimized meaning U is V1 over 2. So if the problem come and he said, well, determine the velocity U when the power was this much, you don't say U is V1 over 2. No, that's only the optimum. And if he's asking out, when my power was this much, what was the U? You calculate the U from the equation. You don't force the optimum velocity on it. You got that? All right. I think we are out of time. Huh? U is always the plate velocity. Yes, that's what will happen. Because again, that built-in wheel, if you make it free to move, it will move with V1. If you let it spin as quickly as it wants, without any load, it will run at V1. But that will give you 0 power. Why? Because the power is not just the speed, it's not just omega. The power is torque time omega. And if you hold it so tight so that it's hardly moving, you get the maximum torque. And sometimes you ask for this. He said, what is the maximum torque? Well, the maximum torque, if you make omega equal 0, then that power equation will tell you the torque that will give you the omega equal 0.
So likewise, does it have a relation with the angle?
Say that again.
So likewise, does it have any relation with the angle?
Which angle? Beta 2?
Which angle is strike?
So he strike always alpha 1 is always 0 because he shoot axially. I mean, he shoot with the plate. But the angle at leaving, that beta 2, you want that beta 2 to be, ideally, you want it to be, if I hit you with this and it bounce back toward me, that will hurt like hell. Because you will get MV and you will get minus MV in the other way. But if it come like this and drop, it will not hurt as much. So what I'm saying is that if we shoot the water and it come back in the opposite direction, that will be the maximum momentum exchange with the plate. But there is a problem with this scenario, because if I shoot this pin, it can come back. But if I shoot a lot of pins on you, there is no chance for them to come back because they are in the way of the incoming one. So ideally, you want beta to be 180, but practically speaking, you can't. You have to let it leave with a little bit of angle so that it can get out of the way of the guys coming. Okay, and so that's why the equation is 1 minus cosine beta 2. He say, if you make it 180, that would be the dream. That would be the dream if you make it 180. And if you do that, if you set beta equal 180, that would be 1 minus minus 1, okay, which make it 2, which then make the power m dot v1 squared over 2. And what does that mean? If the power you extract is half m dot v1 squared, your efficiency is 100%, because you used all the kinetic energy. But when you do this, when you use all the kinetic energy, that means the water come and just like stop and drop. You consumed all the water. It's really like the wind come and just use all his kinetic energy. Okay. All right. Thank you, guys. I'll see you next week. Thank you.